Hi everyone. So welcome to Lattice Semiconductors Developer Conference. So today I'll be sharing on developing PCI solutions with FPGAs. Okay, my name is Nadan Ramachandran and I work as an applications engineering in Lattice Semiconductor. So I have prior experience about 19 years on enabling FPGA itself and focusing on SerDes at PCIe. For today's sharing, what we will be learning itself is we will be looking at what are the solutions that Lattice offers for users to enable PCIe or PCI Express interface in Lattice FPGAs. So at the end of the sharing, you will know what are the collaterals, solutions, reference design, and how to enable PCI interface in Lattice FPGAs. So moving on to the agenda for today. So we will start off with the PCI support in Lattice FPGAs, where I'll give an introduction on how is Lattice FPGAs enabling PCI, how the stacks that is defined in the PCI spec is enabled. Then we'll move on to the documentation and software, where discussions on the collaterals as well as what are the IPs and softwares associated with the collaterals and the tools that is required to enable PCI interface. Then we'll move on to what are the demo designs for PCIe that we are offering. So these demo designs are critical because this will be the base for users to start building a PCI interface using our Lattice FPGAs itself. And then I will touch a bit on our simulation capabilities, and I will end the sharing after discussing some debugging tips and tools before we move on to the end part of the sharing, which is the question and answer session. So one thing to note is we will have the question and answer widget in front of you all. So please do populate that with the questions so I can walk through and find the answers and answer it around. Okay, let's start with the PCI support in Lattice FPGAs. Okay, so the Lattice FPGA supports PCI using the hardened and the soft IP itself. Okay, in this example below, I'm showing how the protocol stack defined by the PCIe is mapped to the hardened IP that is offered within the Lattice FPGAs. So in this example, the device that I've chosen is one of our latest devices, which is the SerDes Pro NX FPGA. So as you can see, the protocol stack for PCIe or PCI Express defines three layers, which is the physical layer, the data link layer, and the transaction layer. The physical layer is the layer which interfaces physically on the board, and it comprises of two layers, which is the electrical subblock and the logical subblock. And then you have the data link layer where the incoming and outgoing data will have some flow control error correction mechanisms. And then you have the transaction layer, which interfaces with your user application. So how these layers are mapped to SerDes Pro NX is shown in this diagram. So for the physical layer, the electrical subblock is implemented using the PMA of the SerDes Pro NX FPGA. So within the PMA, you will have the transmit PLL, the RX CDR, the transmit buffer, the RX buffer, which comprises of equalization circuitries. So on the transmit side, you will have the preemphasis. On the receive side, you will have the CTLE or continuous time linear equalizer and the DFA. So this PMA layer is mainly consists of those analog circuitries that are required to interface on the physical medium or the boards. Even the circuits such as the receiver detection and the signal detect circuit, the analog circuitries that's defined by the PCIe spec is located in the PMA block itself. Okay. For the signals, serial signals that come into this PMA block, it's moved on to the PCS block or the physical coding sublayer block. This block also sits in the physical layer of the PCI stack. It's the logical subblock. So this is implemented using the PCS. Okay, this is also hardened. The physical layer comprises more than just the PMA and the PCS. It also requires pattern generation and LTSSM control. So that's the part of the physical layer which is implemented in the link layer or the hardened PCI Express link layer. This hardened PCI Express link layer is also enabled in the ZX Pro NX, as you can see in the green box here. So besides containing part of the physical layer, it also has the data link layer and the transaction layer. Okay, this is what is in the hardened IP. Let's move on to show what is in the soft IP. So after the link layer, you will have a native TLP interface, which is the parallel data that is going out to the fabric or user logic. And we also have the register access for the link layer and the PCS and PMA. So to enable users to use the PCI hard IP, we have created soft logic that wraps around the hard IP. And the main function of the soft logic itself is for data interface conversion and register interface conversion. So what happens here is from the link layer, if you can see, we have the receive TLP interface and the transmit TLP interface. These are the native parallel data that comes out of the hardened IP. So the soft IP itself offers a conversion or a bridge to change it to either AXI4 streaming interface or a HB Lite streaming interface. And the second function of the soft IP itself is to ensure that all the registers are mapped on different layers like the link layer, the PMA, and the PCS registers. So for PMA, if you have any registers that you want to access on the PLL, for example, the PLL lock, then you can use this. The soft logic has already provided the mapping to go and access the registers in the PMA. And the PCS consists of blocks like word alignment, 8-bit, 10-bit decoders. So those registers related to these blocks are also mapped at the register interface conversion block of the soft logic. So we can access those registers using the LMI and also the APB interface. The link layer also offers a lot more registers, even registers like the config space registers of the endpoint. You can also access them using the LMI or the APB. One of the following slides will actually cover what high level of what are the register content of the link layer. Okay, so that explains the building blocks of the PCI stack and how it's implemented in Lattice FPGA. So moving on, I would like to share what are the different Lattice FPGAs and what is the PCI capability that is offered. So what I shared earlier was the ZX Pro NX, which supports up to PCI Gen 3 by 4. And we offer up to 4 multifunction capability. And we also have a DMA engine, which is implemented in the fabric. You can see I've listed a soft IP there. And then we have the Mac X05T, which supports Gen 2 by 1. And we have Crosslink and ZX NX, which also supports Gen 2 by 1. And the older families like the ECP5, which supports Gen 2 by 4, and ECP3, which supports Gen 1 by 4. So our latest product is Avant, and Avant will be supporting up to Gen 4 with the max link width of by 8. And we have a capability to support up to 8 multifunctions. Avant also will support virtual functions. And a further improvement in Avant is we have actually hardened the DMA engine. So our hardened DMA engine is actually useful for a lower latency DMA operation. Okay, since I've introduced DMA, let me briefly talk about DMA support in PCIe and how important it is. So DMA, or direct memory access, is an efficient way for data transfer because it allows data transfer without the involvement of the processor. Okay, the operation is shown in this diagram. So in short, the DMA engine actually allows the endpoint to send data directly from an attached device to the memory of the host without the processor taking part. So how this is done? Basically, DMA, in this example, we show how a host or a processor transfers memory to the endpoint without involving the processor itself. So the processor has a DMA engine, and it starts the process by the CPU requests a memory transaction to the DMA engine. And the DMA engine will start to request a transfer of memory, and the data is transferred from the storage to the endpoint or from the IO space to the endpoint. So once the transfer completes, then the acknowledgement is sent from the memory to the DMA engine. So the processor is not involved in this process as well. The processor only gets an update from the DMA engine that the completion is completed. A completion update is provided. Okay, so this allows the processor to trigger data transfer without its involvement, so it does not take processing power. So why this can be done for PCIe itself is because the PCIe device driver knows the memory mapping for a particular memory region after the PCIe enumeration. So in PCIe, we have a process called link training and then enumeration. The enumeration is the process where the memory registers or the config space registers are exchanged between the host and the endpoint. Hence, both ends know what is the memory region mapping of a particular endpoint. So this allows the DMA engine or the DMA master to know how much and where to transfer the data, because the information of what is the size and the location is already exchanged during enumeration. So this is basically how a DMA is supported in PCIe. So moving on, I would just like to introduce how the DMA operation is supported in Lattice DMA soft IP itself. Okay. It starts off by the PCI root programming the starting address and the byte count into the DMA engine during the enumeration itself. Okay, after getting the total number of descriptor data from the descriptor queue pointer registers, the DMA read initiator starts reading the descriptors from the descriptor queue. Okay, the moment the reading of the descriptor queue is done, the DMA starts a transaction based on the descriptor data. So if a transaction is completed or aborted, the status data is written to the status queue. Okay, this status queue contains information like the done flag, error flag, length of transfer, and data buffer address offset. So in short, how Lattice incorporates a DMA engine is we have a descriptor queue and a status queue in the memory region. So that's how Lattice actually incorporates a DMA, soft DMA engine into our IP. Okay, moving on. Besides supporting the PCIe, we just want to highlight that for devices like R1 and Ceres Pro NX, we also support reusing the same channels for mix mode. That means you can either choose the channel to be a PCIe and mix with another protocol that has the same reference clock, like Ethernet protocols like 1000 base X or SGMI, or even a standard 8-bit, 10-bit gigabit protocol. So you can mix, one channel has PCIe and the next channel has 8-gig 10-bit. So that's introducing what we have in our, how we support PCI IP at a high level. Then let's move on to what are the documentation and softwares that is required or offered to enable users to use the Lattice FPGAs to implement PCI Express. So for the software part, both the PCI hardened IP and soft IP is enabled using the following IP core. This IP core is available in our Radiant tool. So we have two IP core, which is for PCI by 4 IP or PCI by 1 IP. So PCI by 4 IP is targeted for the newer devices like ZX Pro NX and Mac X05. The PCI by 1 IP is targeted for Crosslink NX and ZX NX. So you can go into the Radeon and you can just click these IPs to create the wrapper that configures all the settings for the soft and hard IP to enable PCIe. And then the usage or the configuration of this PCI by 1 and by 4 is provided in an IP user guide. Both of these IPs itself has its own user guide, and the user guide can be downloaded from the links that will be shared at the reference slide at the end of this presentation slide. Or also, you can even find the user guide from the Radiant tool itself. You just need to go to the IP, and once you click on the IP, there will be an info page where they will be pointed to the user guide. So what this user guide contains is it will show architecture information such as building blocks, clocking, and reset. And the second part is the IP GUI information or the configuration of the IP GUI. What are the parameters that you need to configure, and some tips on what is the selection required. Okay, and the third item that we have also is information on running simulation using the tool generated example design. And the fourth item that is quite critical is all the input output ports that are available to the PCI IP and the register descriptions. We have also added some debugging tips if you are facing issues with PCI link bring up in your hardware. And lastly, we added a design bring up consideration checklist. This is to allow users to check if they are having any issues, or a checklist to check if they have followed all the steps recommended in the user guide. So we have covered on what is the software IP that is required and documentation that is available. Now let's talk about PCI IP implementation in Lattice FPGA. So what Lattice is offering is a simplified PCI implementation in two ways. One way is to start designing leveraging the Lattice demo designs. I'll be sharing next on what are the Lattice demo designs available. Okay, there are 4 different demo designs that have been provided in Lattice website, which includes the PCI driver for Linux and Windows, and the driver source codes are also included. These demo designs are directly portable to Lattice FPGAs. We have demo design user guides to show how you can directly use it, and also simulation test benches with test cases to allow simulations. So you can start designing on your PCI interface by using these 4 different demo designs. Why we have 4, I will later explain. It's catering to the 4 main implementation that we think users will be requiring. So the second option is to start designing from the IP generated example design. Okay, this is not a full demo design that has been hardware generated, but this gives more flexibility. If you're starting from the IP generated example design, you will have more steps, such as you need to perform your IP configuration on your by 1 or by 4 IP GUI itself. You need to refer to the user guide on configuring the IP. And then after you have configured the IP, you can use the design consideration checklist in the user guide to check if everything is according. And then you start to do the functional simulation with the Model Sim Lattice edition. So this functional simulation incorporates a BFM to act as a host. And the Lattice IP generated example design, at a minimum, it will perform link training and complete enumeration. Okay, so if you're designing using the second method, then you can build your user logic and integrate or add test cases to this example design to validate your design itself. Okay, I talked about the design consideration checklist. So this is just a snapshot from our user guide showing what it is. So we have divided the design consideration checklist to two sections. One is for the DMA-based design. If you have enabled the option to enable DMA, then you use this checklist. If you're not using a DMA-based design, then you use the second option, 9.2 section. So here we have kind of provided some tips like, okay, like example, we want you to check if the IP configuration is correct, and then whether the descriptor and status queue are correct. This is for the DMA support. So we have a few steps there that you can use to check whether your design is correct or not. Okay, let's move on to the demo designs that are being offered by Lattice. So these demo designs are available in Lattice website and can be directly used in our Lattice FPGA development kits. There's been hardware tested, and we have simulations incorporated with it. We also have included user guides to show how to use it in hardware and simulation. So we have created 4 different demo designs to showcase the following functionalities. So let me start with the first demo design. This is a basic demo. We call it the basic demo. So this demo design basically demonstrates how to use a read and write on an onboard memory using PCIe. And we also have configured a 7-segment LED using PCIe. So this demo design is very simple. It basically uses a memory write TLP and a memory read TLP to configure onboard memory, as well as allow to modify the 7-segment display that is available in the development kit itself. So why we have such a basic design is, if anyone were to start designing any protocol interface, the first example that you will try to do is try to put a 7-segment display and try to see if you can write using your interface protocol to the 7-segment display. So with that in mind, we created the basic demo for users to start using this. So this basic demo uses the native TLP interface. It doesn't use the AHP Lite or the AXI4 streaming interface. Then moving on, the second demo is a multifunction demo. This demo is basically to showcase the multifunction capability that's offered within the FPGA. So in our design, we have actually implemented 3 different functions, which are GPIO, MDIO, and I2C register on board. The GPIO basically shows a running LED, and it provides real-time interaction with the FPGA. Okay, moving on, we have a more complex design, which is the throughput demo. The throughput demo itself shows the DMA performance between Lattice FPGA and a host system. So we have actually implemented a read-write pattern and a counter data between the host system and the FPGA memory, which is capable of measuring the throughput. And finally, we also have a color bar demo. So this shows the video data transmitting capability between the Lattice FPGA and a host system. So what we do here is we have a simplified bridge that uses a DMA and takes the video frame data continuously from the FPGA and displays it in real time. So we have a color bar, a series of moving color bars that streams the image data using the DMA transfers from the FPGA to the host system. So these are the 4 demos that we are currently offering in our Lattice website. So more details on the demo itself. As you can see here, we have a 7-segment display, and I put the block diagram where you can see we are implementing it using a Gen 3x4, and the PCI IP itself sends the native signal to a PCI application wrapper that is created, whereby we will send the information to a 7-segment display or to a RAM. So this allows the 7-segment display to be programmed to whatever value that we are putting in the GUI software itself. So we have implemented this using the bar memory driver itself. Okay, it's a very simple design. Okay, for the multifunction demo itself, what we have done is we have enabled multifunction in our PCI hard IP, and we have implemented a function arbiter with different functions like I2C, GPIO, or even MDIO. So here you can see in GPIO, we have actually taking the inputs from the deep switch. We have 5 deep switches, and based on that input, we can determine whether the selection is 0 or 1. And we have also implemented a running counter, whereby when you click the set counter, it will start a running counter, and the LEDs in the onboard on the boards will start running. So we also have a I2C interface where we can show the functionality with a camera module on board. Okay, the next demo is a throughput demo. This demo is more complicated. We are using a DMA engine, and we are using a AHB master. And then we have the AHB write arbiter between a memory write and memory read. So a data checker is implemented in the software application running on the host. So what happens is you can perform a DMA write, and a data checker checks whether the DMA write gets through. So for DMA read, the data moves from PC to FPGA memory. So we also have implemented a data checker to be in the FPGA. Okay, the application software calculates the throughput based on the data transfer. The last design that we have is the PCI color bar demo. Okay, this design implements a register space to configure the DMA and get the status of the transfer and throughput achieved. So what we have here is we are sending a video interface in terms of a video data in terms of color bar. It's a moving color bar. So we have a FIFO wrapper that implements a video timing generator and a bar pattern source to generate the bar pattern for the DMA write operation. The video generation will take place throughout, regardless if the AHP is ready or not to receive the data. So we couldn't stop the way we created this code, we couldn't stop the video generation. So we also implemented a ping pong memory wrapper in the design to act as a buffer to allow the HP to receive the data when it's ready only, because the data is going throughout without any checking whether the HP interface is ready or not. Okay, so those are the 4 basic demo designs that we have offered in Lattice website. And we have also enabled the simulation test cases for users to understand better, or if they want to improvise or use the demo designs and build on top of it. So for simulation itself, for PCIe, it requires a link partner to link up to achieve the operation state, or the L0, and complete enumeration. So to do this, we require a BFM as a link partner. So currently for Lattice PCI IP, a BFM is provided as part of the example design or the demo designs. So when you generate the IP itself, an example design is generated. And we also have instruction how to run the simulation in both the example design or the demo designs in the user guides. So the functional simulation will start with the process of initiating PCI link up, which involves all the basic PCIe LTSSM states like detect, polling, configuration, and go into link up. So for the analog blocks, we have a behavior model to represent that. And after the link up, we also have the enumeration process. The simulation will show like the config space registers are being exchanged, and the bus device and function is also provided. So for the analog circuits, it also needs to be modeled. So we have included a behavior model, and this could impact a simulation time. But with the latest version for the PCIe by 1 and PCIe by 4 IP generated using the example design, we are able to complete the link up and enumeration within 30 minutes using the model sim lattice addition. This is quite a fast time for link up using a model sim lattice addition. Model sim lattice addition requires very little memory because it only processes around 5,000 instances. So we have improved the BFM and we have watermarked the BFM to ensure that we can link up within 30 minutes. So this will ensure that the simulation does not take time, or you do not need to use a powerful simulation tool. You can move on with the model sim lattice itself. Okay, moving on to the IP generated example design. This is just a block diagram showing how the IP generated example design is. So you have a BFM, you have our Lattice PCI IP acting as an endpoint, and you have two options, whether you want to generate an example design for a DMA enabled configuration or non-DMA enabled configuration. That's on the simulation. And after you have used our demo designs to build your updated designs and run the simulation, the next part is once you go into bringing up the hardware, you might face some PCI link up issues or enumeration issues. So here I'm going to share what are the solutions that Lattice offers for debugging the issues itself and the tools that we have. So in our user guide, we have provided flowcharts that shows common issues like if you're facing a receiver detection failure, what are the items to check? If receiver detection is a very common failure that sometimes you can observe when you're bringing up a board for the first time. Things like checking the AC coupling caps or what are the status signals to look at. We have included that in our user guide. And then we have also provided some details on what are the link training issues that you could be seeing and what are the steps that you need to take to resolve it. For example, if you see a link training issue whereby you see your LTSSM toggling between recovery to L0 to recovery constantly for the speed of gentry, then what do you need to do? It could, if you see that it's going through recovery equalization continuously, it could be caused by the channel loss is too high. So we could recommend doing some things like limiting the presets or something like that. These are all documented in the chapter 8. So these are the steps on debugging. Okay, as for the register list, we offer a range of registers for debugging. Okay, so within the PCI link layer, hardened PCI link layer itself, there's a lot of registers, and we have the registers related that shows the LTSSM states. What are the physical layer states that we need to look at? Like for example, if you want to know if it's an electrical idle exit condition triggered, then we have registers for that. Okay, and equalization configurations, power management related registers, and the TLP interface. We also like the parallel bus, the TLP interface. It has the start of packet indicator, end of packet, receiver buffer overflow, underflow, and data link layer related registers, whether there's a DLLP update, progress acknowledgement. Those type of information are captured as registers. So this is also available in the chapter 5 of the user guide. Okay, these are the hardened IP core registers, which tells how the hardened IP core is behaving. But the debug could be beyond an issue on the hardened IP core. It could be related to something missing in the enumeration or the configuration of the PCI IP itself. So for this, we have the PCI Express configuration space registers mapped into our hardened link layer, which includes the capability and extended capability registers. So if you're not able to link up, you will not be able to use tools like LSPCI or Teledyne Recroy to read the config space registers. So you can look at this capability and extended capability registers from the endpoint itself. Power management registers, the advanced error reporting capability registers, MSI and MSIX capability registers, and the other capability registers like the ARI, resizable bar capability, and many others. So besides the hardened link layer registers, we also have the soft IP registers related to the DMA, the HP Lite, and the interrupt mask registers. So besides, if we do not have, if the link is not up and you do not have the capability to put a protocol analyzer, you can use the registers that is offered within the PCI IP to aid in debugging. Okay. So we have an additional tool as part of our reveal analyzer and control, which incorporates a logic analyzer equivalent feature where you can probe the internal wires and ports. As you can see here, there's a snapshot of a logic analyzer type tool. Okay, and in our Radiant 2023, we have a section, a capability to look at the PCI link layer and file register status without reading them over the LMI interface. You just need to enable a single button, the PCI LL option, and you will be able to see like the transmit settings, what is your amplitude, receive settings, and also the data link layer status. So for example, you can see the TLP receive, TLP fire error, and all those. There are many more of these. And you can see there's a PCI LL there. Can you see you have the physical layer link status, link speed, LTSSM state. So all this will be kind of like a link inspector to say where is your link at what at a time of probing itself. Okay, so besides this, you also have access to the LMI or APB bus to read and write the PCI link layer and file registers. So besides that debugging tools that we provide, we also have the capability to monitor the eye. Okay, so we can monitor the eye when PCI is linked up. This is non-destructive. That means it can be turned on without bringing the link to link down. It can be running in PCI link up mode and you still can plot the eye. This can be used as a relative comparison if you have some channels failing and some channels passing. So you can do a relative comparison to see whether the eye is open or closed, to know whether the issue is related to the signal integrity of the channels itself. Okay, and the next item is I've included the references in the Lattice website for different the user guides and the designs for the demo design, for the 4 demo designs that I've introduced. Okay, in summary, what we have learned today is Lattice enables PCI solution Nexus and L1 platforms, targeting support up to Gen 3 by 4 for Nexus platform and Gen 4 by 8 for L1 platforms. We also have introduced the IPs and demo designs provided, and the simulation test benches and hardware ready designs that are available, the hardware bring up checklist, and the PCI interface debug that is available. Okay, so that concludes our sharing for today. So let me look at some of the questions that I've got from the widget window itself. Okay, the first question is, what is the limitation of amount of functions for your devices? Okay, this information is actually available in one of our slides. Okay, we have, for most of our devices, which is CertX Pro NX, Crosslink NX, Mac X05 NX, we have up to four functions itself. So multifunction up to 4 is supported. But for Avant, we have up to 8 functions. And for Avant, we are also incorporating SRIOB, which enables virtual functions. Okay, that's the first question. Let's move on to the second question. Okay, the second question is, how can I debug if the link is down and it's related to the signal integrity issue on the channel? Okay, this is an interesting question. I probably covered that on the last slide. So one of the features that is offered in our debugging tools is the eye monitor. You can enable the eye monitor and compare between one channel to another to see if the channels that are linked down are having a worse eye compared to channels that can link up. If you're using only a PCIe by one configuration, then probably you need to look at multiple boards to compare. Okay. Third question, is MSI interrupt enabled in Lattice PCIe? The answer for that is yes, it is available. We are supporting all the three interrupts, which is the legacy interrupt, MSI interrupt, and MSI X interrupt. One point to note is in one of our demo designs, which is the DMA throughput, we have actually created the logic to enable MSI generation on the endpoint. And the driver supports triggers the MSI generation from the endpoint itself. So the simulation test case for the DMA throughput design also showcases how this is done. Okay. The next question is, how do I identify what is the bus device function of the endpoint if I do not have a capability of scanning the entire root ports? Okay, the question is, how can a user identify what is the bus device function of the endpoint if the information from the host is not available? There are tools that you can run on the host, such as LSPCI on Linux or Teledyne LaCroix on Windows platform. But if you don't have these tools, or there's a limitation on the tools or capability of the host, then you can read the bus device function using the UCFG interface that is offered within the Lattice IP itself. The UCFG interface can access the bus device function. This information is also available in the user guide. Okay, the next question is, are we supporting BRA, prefetchable and non-prefetchable memory itself? The answer for this is yes. Non-prefetchable and prefetchable memory is supported as well. Okay, that's the questions that I have got from the widget for now. So let me see if there's any other questions. No, I can't see any other questions as of now. So I think that's all for my sharing today. I hope that you have got some useful information on how to enable our PCIe solution using Lattice FPGAs. And hope you all enjoy the next sharing in the Lattice Developer Conference. Thank you very much.